So if we think about for a moment what we've got, that as I said, each one of these delta z's has a normal distribution with a mean of 0 and a variance of h. So delta z squared, well, what is that? A normal squared looks like a chi-squared distribution. But the one thing that we can say about z squared is that if I take the expected value of it, I know what it is. The expected value of every one of those square terms is h. Why? Because the expected value of delta z squared is by definition the variance of delta z. So it's h. So the expected value of this mysterious sum of squares, I'll just denote it delta zi squared, where delta zi is the change in z over the ith interval. The expectation of this sum is nh, and that's t, right? By definition, nh is t. However, the sum of these squares is a random variable. And you may recognize that some of what I'm now going to say will be reminiscent of an argument I gave about where the minus 1/2 sigma squared t adjustment came from in the mean adjustment in geometric Brownian motion, where we were using the Taylor series approximation of the log function, and I was dealing with sums of squares of normal random variables. We're going to have the same discussion here. It's the same point. The expected value of that sum is a simple number to calculate. Delta z is normal, has a mean of t. The interesting thing, though, is that even though the sum of these squares, it's a random variable, the point is the variability of that random variable goes to 0. That the variance of this sum of squares goes to 0 when h goes to 0. So this turns out that while we can say the sum of squares of these delta z's has a mean of t, more importantly, the sum of squares become less and less random as n gets big, as h gets small. Less and less random to the point where the variance of that random variable goes to 0. So we then end up with the conclusion that, in fact, as n goes to infinity, the sum of those squares is exactly t. Now, if we approximate y, remember yi is the change in z. If we let y be plus or minus 1, instead of using the normal distribution for y, we define it as the binomial approximation, well, then it's apparent, because then y squared is 1 always, and we just get a limit of a sum of nh's, which is t. I gave you the somewhat more general argument that if y's are normal, it's still the case that the sum of square changes in Brownian motion has a fixed value of t, even when the y's are normally distributed. It's easy to see that the expected value of that sum is t. The hard part, which I will not do, is that the variance of that sum, in fact, goes to 0. That's what I say here in the last bullet, that when yt is normal, the analysis is more subtle. Not that the mean of the sum is t, it's that the variance of the sum goes to 0. It's a subtle and somewhat difficult argument.